Okay, second lesson of the volume and area unit. This one is about areas of regular polygons and composites. Composites are nothing to be scared about. Composites just mean this is the section where they throw in all kinds of funky shapes that are made up of other shapes, and you just have to cut them up and add them together, basically. Regular polygons might be kind of new. It's a little complicated because it's so general, but when you're done, I guess the power of that being so general is that it'll work on lots of stuff. Okay, regular polygons we've defined before. Hopefully you remember what those are. All the angles are the same and all the sides are the same, like this hexagon shown here. For the formula for the area of this, what they do is they chop it into a bunch of little triangles like this. And you can always do this with regular polygons. You can chop them up into these little right triangles. We want right triangles and not maybe isosceles triangles like that, because right triangles we need to know the height, and the height, or any triangle, we need to know the height. We need to have stuff that's perpendicular in order to find area, as you learned in the last lesson. So we actually want to chop them up like this. And you can always chop regular polygons into right triangles like this. You take the midpoint of any side, and that will make a right triangle as such. This thing is the new term we have to define. This thing, they use A for this. This is called the apothem. This thing they technically call a radius. I don't know if you have a problem with that being called a radius because this is not a circle. Anyway, those are the two things that are emanating from the center. They are, of course, different. It's not going to be like a radius of a circle. This length, this R, is longer than this length A. You can tell that by the fact that this is a right triangle. A squared plus half the side squared has to equal R squared, so that's how you find them. Anyway, the central angle of a regular polygon has its vertex at the center of the polygon, and its sides pass through the consecutive vertices of the polygon. So a central angle would be like, if I can mess this up really fast. Oh, if that was a straight line. Sorry. It's hard to draw straight lines with this tablet thing that I use. This would be like the x degrees. This would be the central angle we're talking about. Let me get rid of that now that you've seen it, because it's going to mess up the next part of the formula. So each one of those angles gets cut in half to form this angle up here. Like AOH, that has to be 30 in a hexagon. In a pentagon, that would be different. In an octagon, that would be different. But you can always find it by dividing the number of sides into 360 and then cut that in half for this one. So the amazing thing about all this is once you've got, if you find all these little areas and you add them all up and you account for the number of sides n, some things start to cancel out, and the area of the whole thing is always just this, half AP. Half, that kind of comes from the formula for the triangle area. A, which is this thing here. P, that accounts for the number of sides. That actually takes into account how many sides there are and how long they are. So what's really nice is how this formula, all these little triangles, they all add up. There's this funky degree in the middle, and there's n times 2 of these right triangles. I mean, it's a big mess, actually, and it all condenses or simplifies down to this AP. It doesn't matter how many sides there are. You just need the perimeter and then this little thing right here. Okay, that was a lot of talking. It's easier than it sounds. Okay, so I wrote that again. So you can see that. The above formula is just an extension of the triangle area formula. Okay, I said that already. So yeah, the triangle area, so the area of this hexagon is actually 6 of these triangles that are the size of DOC, or the size of AOB. It's 6 of those, but the base is AB times 6, which is, sorry, the base is AB of that triangle. There are 6 of them. And if you think about all those bases added together, that would actually be the perimeter. So again, it simplifies the half AP. I could do a formalized proof of that in class if you'd like. It tells you the apothem here. It's 8. And that's all it says. It just says the apothem's 8. Find the area of the hexagon. Well, the area of the hexagon is half AP. Well, that's lovely. That's nice and simple. Half times 8 times what? I got to find P. Well, how on earth am I going to find that perimeter? Well, the perimeter is 6 of these things, or 6 of these ABs, and I don't have that side. But I do know that this is a hexagon, and I have one side of this little triangle here, and I can figure this out. This, remember we just learned this a second ago. We said this a second ago. This has to be 30 degrees because this is a hexagon. This has to be 30 degrees because of a couple of reasons. We just said on the other page that AOH has to be 60 because there's 6 triangles like this in the whole hexagon. If I divided all these by, divided 360 into this whole circle, I'd find out that each one of these is 60. Divide that in half, I know this has to be 30. Essentially, those little angles there in the right triangle always have to be 360 divided by twice the number of sides. So in this case, that'd be 360 divided by 12. There's 12 of these little right triangles in the whole thing. If I were to cut these all in half and draw in all the apothems, there'd actually be 12 of those. So you can do that either way. You can divide by 6 and then divide by 2, or you can just divide by 12. This has to be 30. So this is our old friend, the 30, 60, 90 triangle. So if that's 8, okay, that's the weird one. That's the one that's supposed to have square root of 3 in it. Okay, so this is supposed to be the short side times the square root of 3. So that means this side down here is that divided by the square root of 3. So when I multiply this by square root of 3, it turns into 8. I need perimeter, right? So that's 8 divided by the square root of 3. This whole side, or this whole side, A to B, would be, or any of these sides, would be 16 divided by the square root of 3. So that's what each side of this whole thing is. That's what this is. Also, not really important. I needed this side. So the perimeter of this thing is 6 of those. That whole thing is the perimeter. So let's write that one step. All right, calculator time. Actually, I could do this without a calculator. It's almost easier. 4 times 6 times 16 over the square root of 3. Yeah, okay, maybe I do need a calculator. 4 times 6 times 16. Sorry, it's almost quicker to do that than plus. 384 divided by the square root of 3. Finally, a regular pentagon with radius 20. Let me draw a nice pentagon. All right, pentagon with radius 20. All right, this is not perfect, but it's not bad. Okay, that's supposed to be 20. I'm going to need this too, so let me draw this in. All right, I'll get off my perfect line tool. Okay, radius is supposed to be 20, so that would be this thing here. I'm supposed to find this area. Okay, great. Well, yeah, area is half AP. Well, I don't have A and I don't have P. All I have is this 20 over here. Well, this is a regular pentagon, so I can figure out everything I need to know about this little triangle here. This little angle in here is, well, there's 10 of these in the entire, if you were to draw all of those, there'd be 10 of these little triangles in the entire thing. So this is 360 divided by 10, or I know that's exactly 36 degrees. I need this one. I need, oh, it's A and it's actually adjacent. Oh, that's lovely. It's the apothem, but it's also adjacent to 36. Great. So I have this thing involved. I have this thing involved. That's hypotenuse adjacent. This looks like cosine. Cosine is adjacent over hypotenuse. So the cosine of 36 is adjacent over hypotenuse. Lovely. And so then I just need perimeter. Oh, for perimeter, I need to know this little guy down here too, because then I'll double that for the length of the side and then multiply that around to find the perimeter. X, at this point, I could say is involved with sine with 20. I know that the sine is opposite divided by hypotenuse, so the sine of 36 is x over 20. So 20 sine 36. Oh, that's just too cute, isn't it? This is x. So this is 20 sine 36. This is 20 cosine 36. That's going to come up a lot. You might get surprisingly fast at memorizing how that works. If this is the angle we're looking for, and that's hypotenuse, this is 20 times the cosine of that angle. This is 20 times the side of that angle. You don't have to know that, but that'd be great if you did. So this entire side, I'm going to work in exacts today. I feel like working in exacts. So if this is 20 times the sine of 36, this whole thing is double that, which would be 40 times the sine of 36. Sorry if that annoys you, but that's what I'm going to do here. I'll use the calculator just at the end. So this is half times A, which is 20 cosine 36, times perimeter, which is 5 of these 40 times sine 36's. All right, let's put that in the calculator. All right, put that in the calculator, and I get this lovely, this really lovely exact value for that. You'll start to notice that with regular polygons a lot. Cosine 36 actually has an exact value, just kind of like cosine and sine of 30 and 60 did with square roots of 3 and 45 and square roots of 2, because it's a regular polygon. Remember, this was a pentagon, so surprisingly enough, there's some square roots of 5 involved. You probably don't want that. You probably want the approximate value, so let's do that. 951.06. So this is squiggly equal 951.06. Okay. All right, composite figure. Okay, so this is just when they start adding up things that are little areas stuck together, basically. The area of a region is the sum of the areas of its non-overlapping parts. This is a total middle school type thing you've seen before. So they have this funky shape that looks like, I don't know, what you'd call that, a messed up basketball court lane or a track or something. Find the area of this whole entire thing. That includes this thing over here. So we're just going to chop it up into stuff we can find the area of. First of all, we have a trapezoid here. I would think of this as a trapezoid plus a semicircle. I also kind of like it if you were to show your work this way. I'm going to find this area, and then I'm going to add on this area. I kind of like people showing that in there. That's not a D, that's a semicircle picture, in their work, so then I can tell what's going on. This is kind of in my way, isn't it? Whoa, I am going to do that, make myself some more room. Okay, so we need the trapezoid. So the trapezoid is base 1 plus base 2, whoops, base 2, divided by 2 times the height. Oh gosh, I need the height. I need this entire thing. You know, I'm going to call this D for diameter. I need that diameter. And then I'm going to add on half of this circle. Oh gosh. I'm going to call that diameter and call this radius. Plus half of, oh, have we done area of a circle before? I don't think we have. This unit, but you know that's pi r squared, so that's not it. All right, so I need to know this diameter. I need to know this radius. Those aren't impossible to find. If this is 15, okay, I could involve that because this 15 is here, but I haven't used it. It's not directly part of any formula, but I can use that to find this diameter because that would be the same, right? All right, if this is 22 and this is 31, I can figure out this part hanging out over here, and then I can do Pythagorean theorem. That's 22. This is 31. This must be 9. Oh, this is the 3, 4, 5 triangle. That must be 12. Check me out with Pythagorean theorem. 9 squared plus d squared ought to be 15 squared. Use your calculator. I'm pretty sure that's right. So if that's 12, these guys are 6. Let me fill in the formula. Okay, and so I've done that. Put the numbers in the formula. I get 318 plus 18 pi. What's kind of nice about this exact answer is because of that pi there, it leaves the two things separately, so I can kind of tell that the trapezoid part was 318 and the semicircle part was 18 pi. You don't have to do that, but this worked out exactly that way, so it was fine to leave it like that. Okay, last one. Find the area of this crazy V shape. That's 1. This is, well, we could try to find the area of this crazy, what is this, a pentagon, and then multiply by 2, or we could find the huge outside trapezoid and try to subtract this little triangle on the inside. I kind of like that. Let's say the plan here is going to be trapezoid minus triangle, and that's not really clear, so I'm going to draw that a little bit more. If I'm showing my work here, whoa, that's not a great one, minus that triangle that's pointed that way. I think that would be easier to do that. All right, so trapezoid is base 1 plus base 2 divided by 2, so this whole base is 12. Oh, nice brace. That's 12, and that's 8. So 12 plus 8 divided by 2 plus, oh wait, times the height. And the height I don't know. I would need to know this. Let's call this x. Times the height, which would be x plus 1. Minus the triangle, which is half times that little triangle's base times that little triangle's height. Okay. Notice I've used everything in this picture. It's kind of a hint. And I need to find x, except that I haven't used the 6. The 6 is going to help me in this little right triangle. This is 2. These better be 1. It didn't tell me that's a... oh yeah, it is an isosceles triangle, so I'm sure that's working. So that's 1 and 6. I can use Pythagorean theorem to find out the x here. 1 squared plus x squared equals 6 squared. So x is the square root of 35. Let me fill that in the formula. So I just simplified the 12 plus 8 divided by 2, that's 10, and then the half times 2 cancels. If I type that in the calculator, the exact answer is the square root of 9 times square root of 35 plus 10, or, approximately that. So you can write it either way. Again, I hope I haven't made any mistakes. Catch them for me, and I will give you a prize. All right, see you in class. Bye.